Yeah, just
Congrats, you moved to
Oh,
recently.
thanks. Yeah. Hi, hello, Alex. That's David. Third year, wow. Like twice.
Twice, yeah.
Yeah. How's everything going there? Okay. Okay, good. Yes, we got to know.
Yes.
Okay.
What about you?
I have a few first years working with me. Yeah, I really get many students at UVA.
Oh, I see. That's the transfer.
Yeah, so I have one student that's going to transfer in the fall.
I see.
Yeah, yeah. But there's a couple first years.
I see.
That's it. None of them are crypto, so they're more all theory. So a little bit of wrapping up to this.
Oh, I see.
Yeah, yeah. So we're working with our best students at the moment. So,
That's good.
yeah. So.
All right. Welcome to the second talk today. And this is part one of a double header with Mark Zhandry from NTT and Princeton University on clonable quantum cryptography. So I'll try and get the mic to you if you have a question so everyone can hear it and it gets registered on the video.
Great, thank you. Yeah, so today I'm just going to give sort of a brief high-level overview of sort of various aspects of quantum cryptography where the goal is to get some sort of unclonability security. All right, so the starting point is naturally the quantum no cloning theorem, which says that if you have a quantum state, but you don't know anything about it, you're just handed the quantum state, that you can't produce two identical copies of that state. And contrast this to the classical setting where information can easily be copied just by writing it down twice. So the beginning of the field of quantum cryptography is actually due to Wisner, who said, hey, well, if quantum states are unclonable, why don't we use them as currency? So your banknote is some quantum state. By the unclonability of quantum states, you now can't copy your money. Right. So then, well, I should say that after Wisner's proposal, quantum cryptography kind of went in a different direction, quantum key distribution and stuff like that. But sort of in the last 10 to 15 years, we've come back to thinking about these unclonable properties. So the one that I'm going to be spending the most time talking about is going to be public key quantum money. And this overcomes a limitation of Wisner's scheme. So the thing is that with Wisner's scheme, the banknote is just this quantum state. The whole reason that it's unclonable is that the general public doesn't know what the state is supposed to be. So then there's a question, how do you actually verify your, someone hands you a quantum state and claims it's a banknote. How do you actually verify that it was a legitimate banknote? And with Wisner's scheme, there's no way to do this. The only thing you can do basically is send the money back to the mint. They will actually know what the state was, and using that knowledge, they can check for you. But that's obviously not desirable. You don't want every single transaction that happens with your money system to have to go through the mint. So really what you want is a quantum state where it's unclonable, so it can be used as money, but you also want public verification so that everyone has the ability to tell whether they have the right quantum state, but still, even with that ability, they can't copy it. And a consequence of insisting on public verification with no cloning is that there's going to be a cloning aspect, but there's also going to be a computational security aspect. And the reason is if you were computationally unbounded and you had public verification, so if you're able to verify if you have the correct quantum state, but you're also computationally unbounded, you can basically just do a brute force search. Just plug in an arbitrary state, run the verification, see if it succeeds. Once it does, you have the correct state. So with public key quantum money, we enter this sort of interesting regime where we're combining the information theory that comes from quantum mechanics with computational security. And this was really not a well-studied area until starting about 10 to 15 years ago. Questions that combined quantum with computational security. Okay, so in this talk, I will give a survey of the landscape of basically different cryptographic objects that have this flavor of no cloning, but also seem to come with a computational aspect. And as we'll see, there are many challenges to actually combining these different areas together. So I should mention that there are a lot of ways in which quantum computation and quantum information will impact crypto, and I'm not going to talk about many of them. So I'm just listing a couple impacts of quantum for crypto that we won't be discussing today. So one is you can improve the assumptions needed for crypto. There are a couple recent works that were able to improve the assumptions needed for secure multi-party computation from the classical setting to something less, to basically the minimal assumption in the quantum setting. Quantum presents many proof challenges. If your adversary is now a quantum algorithm, we can't necessarily reason about our quantum algorithms the same way we could classically. And there are sort of two main areas where this comes up. One is if your proof involves running the adversary and then rewinding them. And it's now well known, and this has to do with the no cloning principle, but it's now well known that this is problematic quantumly, though we now have a good number of techniques for how to nevertheless do rewinding quantumly. Another one is this thing called the random oracle model. It's another proof technique used in classical cryptography. And it turns out when you sort of consider this oracle classically, you have to allow quantum queries to the oracle. And now, a lot of our classical proof techniques break. And then finally, there's a class of attacks you might call superposition attacks, where the something like a pseudorandom function or a signature or something like that, where the adversary actually gets to query the challenger on a superposition of messages instead of a single message. And this also breaks many of the proof techniques. Overcome this issue. But yeah, so I won't be talking about these. I'm really going to be focusing on no cloning applications to crypto. All right, so these are going to be the kind of three broad areas I'll be talking about today. So the first is public key quantum money, and that the public key quantum money plus an aside about the current state of obfuscation will take up, I think, the whole morning. And then in the afternoon, I'll talk about these other two, copy protection and what I'll call revocable cryptography. Okay. Key quantum money. So our focus today is going to be on something called a mini scheme. So when I talk about quantum money, I'm really just going to mean mini scheme. This was a notion coined by Aaronson and Cristiano. And really think of a mini scheme as just a setting of quantum money where there is just one banknote. That's it. One banknote. It has a serial number and nothing else. And fortunately, we have Aaronson and Cristiano proved that with a mini scheme plus digital signatures gives you a full scheme, and that this is I won't really talk about that. It's not too hard, but really the bulk of the difficulty of getting a quantum money scheme really boils down to constructing a mini scheme. So what is a mini scheme? So there's two algorithms. So there's a gen algorithm that samples a banknote and a serial number for that banknote. And you can think of the serial number as a public key. I might call it that as well. So you sample, so gen samples a banknote and a serial number. And ver is just the verifier, takes as input a supposed banknote and the serial number, and either accepts or rejects. We have the obvious correctness requirement that an honest banknote serial number pair output by Jen should verify. And then we have the security over here where the adversary is given the banknote and serial number outputted by Jen. And what the adversary has to do is produce two banknotes that each pass verification with respect to the same serial number. Right. And so what we want is that there's no computationally efficient adversary that can win this game.
Mark?
Yeah.
Is this reusable?
So I'm not going to stipulate it in the definition, but it turns out it's sort of automatically reusable because you can sort of once you have a verification pass, you actually know you can implement your verification in such a way that it preserves the banknote. This is gentle measurement. So yeah, we don't need to sort of add that as a property. That's something you clearly want with your money system, and you get it for free with both if you implement Ver the right way. Okay. So it turns out that there have been a number of proposals for public key quantum money in the last I guess 13 years, but really they're best categorized as candidates. And the reason is that in pretty much all of these works, a construction is proposed, and then there's little done to justify the assumption, other than like, okay, maybe it's loosely based on some problem that appears hard classically, maybe even one that's well studied and believed to be hard classically, but there's no reduction, there's no proof that the scheme is secure if some widely believed conjecture holds. Instead, in most of these cases, the scheme really just is conjectured, and then it's left to others to try to cryptanalyze it. And as a consequence, it actually turns out that a number of these proposals have been broken. Often, sometimes they required some work, sometimes it happened really fast. And then other ones have remained. So this one based on knots, as far as I know, hasn't been cryptanalyzed, but there's also been, as far as I'm aware, not a lot of literature trying to break it. There's some more recent construction based on modular forms, and then a much more recent one based on quaternion algebras. And really, there's been very little, compared to like traditional cryptographic assumptions like the hardness of factoring, there have been very little work done trying to analyze these schemes. So I don't know. I
mean, Christiana and I did prove our scheme secure under an
Yes.
assumption that the assumption was false.
Yes. Yeah. So the one exception. So there's basically two exceptions to what I said about these schemes being not having reduction. So the Aronson and Cristiano scheme did in fact have a reduction. I'll be talking more about that. And then there's I didn't put it on here, but we can basically instantiate the Aronson-Cristiano scheme, and I'll talk about this more later, using indistinguishability obfuscation. And there, maybe you question the existence of indistinguishability obfuscation, but at least there's an assumption that might hold, and we have a proof. Okay, so why is quantum money so hard? I mean, one might just be getting the right structures in order to facilitate quantum money seems challenging. But I think there's also sort of a more fundamental reason why quantum money is hard, or at least why building a quantum money scheme with provable security is hard. And so here's kind of the first challenge is, okay, suppose that I have a security proof. What does a security proof look like? I have some conjectured hard problem. It has to be quantum hard or believed to be quantum hard. It's something widely studied, and just by the nature of the fact that most cryptographers spent most of their time in the classical world, a hard problem that's been widely studied is probably a classically defined problem. So it's it's a problem like, okay, well, factoring would be a bad example, but if a problem like CIS or LWE it's a classical statement, and you're just hoping that it's hard for quantum attackers. Then you have a reduction, and what the reduction promises is to take any adversary for the quantum money scheme and use it to solve the hard problem. So so why does this present the problem for quantum money? Well, suppose I had such a reduction, some quantum money scheme and such a reduction. Well, notice that remember we said that the hard problem is classically defined, which means that the instance of the problem is actually a classical string. I can copy that. It's just bits, right? I can copy that as much as I want. So what I'm going to do is I'm going to take my hypothetical reduction and I'm going to run it twice on the same string. Well, what does the reduction spit out? It spits out an input to the adversary for quantum money. What does the adversary get as input? It gets as input a banknote and a serial number. So the reduction spits out a banknote and a serial number. This reduction also spits out a banknote and a serial number. And now notice that I have two banknotes with respect to some serial number. And that's exactly what the reduction is hoping to get from the adversary in order to allow it to solve the hard problem. So I just take my first reduction up there. I'm going to throw him away. I don't even need him anymore. I just use the fact that he spat out a banknote and a serial number. I use that second copy of the banknote and feed it into the reduction down here. And by the guarantees of the reduction, it would seem, the reduction, from the reduction's point of view, it looks like it's interfacing with an adversary for the quantum money scheme. So the reduction should actually break the hard problem. Right. So So this is a sort of a conceptual barrier to trying to prove the hardness of quantum or the security of quantum money. And I guess there's also another conceptual barrier that's a bit more high level, which is that no cloning comes from information theory, right? It says if I give you an unknown quantum state that you can't clone it. On the other hand, as we already said, the quantum money state is actually information theoretically clonable. From an information theoretic perspective, we don't have no cloning. It's totally determined by the public key. And so somehow we need to combine these information theoretic techniques that allow us to prove something unclonable with the computational techniques of reductions and stuff like that, in order to take a state that is information theoretically unclonable and actually information theoretically clonable and actually justify that it is computationally unclonable. Okay, so we basically have three strategies to do this right now. What are the strategies? So the first is to move into a relativized setting, to assume that you have an oracle of a particular structure. And this was done by Aronson and Cristiano. And some of the more recent schemes also have proofs relative to oracles. So the pro here is that relative to an oracle, it turns out you can actually get unconditional security. So these schemes actually have an unconditional security proof that relative to this oracle, they are in fact quantum money schemes, secure quantum money schemes. The obvious problem though is that you need to somehow actually instantiate this oracle in the real world. So this oracle might be very structured. So there's a question of even how might you find this structure needed for the oracle in the real world. And then even if you have some structure in the real world that sort of mimics the oracle, you have to justify that it's as good as a black box, that essentially the only thing that an adversary can do is query this function f on various inputs or superpositions of inputs, and not do something more sophisticated with the non-black box implementation. So we can get unconditional security, but it's not always clear how to get this in the real world. And in particular, Aronson and Cristiano, so they gave oracles. They said it proves that you get unconditional security, and then they gave a candidate implementation, which ultimately it turned out it was not as good as a black box and was cryptic. Okay, so here's another strategy that dates back to work of Ludomirsky and others, and then I kind of recoined the term a couple years ago. And the idea is that, well, maybe I'll go back to the previous slide. So if we look here, I don't know if anyone caught what I did, but I cheated a little. in the sense that I assume that the reduction both times I ran it outputted the same serial number, right? And what if the reduction outputted a different serial number when I run it here and a different serial number when I run it down there? Well, then the banknotes that I get from the two runs of the reduction are not valid with respect to the same serial number. And so then you know, the input to the reduction down here will not actually look like a valid adversary, and the reduction and the this box here will not actually break the hard problem. So what we need then, if we're going to follow this kind of strategy, what we need is that the reduction that we have outputs different serial numbers every time we run it. And it's actually worse than that. It's not just that a particular reduction we chose outputs different serial numbers every time we run it. It's no matter what reduction you could come up with, every time you run the reduction, even on the same classical string here, you get a different serial number. So we're almost thinking of the reduction as an adversary now. And if you formalize this, what you get is this thing called quantum lightning, where so this adversary, now think of it as the reduction. The adversary, or think of it as the sort of running the reduction twice, I guess. And it should be impossible for the adversary to come up with some serial number and two banknotes that verify with respect to that serial number. Right. So if we could say that this was impossible for an adversary to do this, it would imply that whatever reduction we chose must output two different serial numbers if I run it twice. Yes, question? Yeah, so it would, I mean, it could be deterministic, it could not be deterministic. For this kind of approach, it's sort of inherent that the reduction would not be deterministic.
But yeah, because otherwise I don't see how you're going to.
Exactly. Right. So it's sort of inherently probabilistic to the extent that there's no way to run the reduction deterministically. No way to, you know, like classically, you could always run the reduction deterministically by fixing the random points. And here, what we were saying basically is no matter what you do to run the reduction, it's always going to be randomized in some way. Right. So this is something called quantum lightning. And if you notice, quantum lightning is actually stronger than quantum money. So in this, right. So in quantum money, it's the same goal of the adversary, except the adversary is told what the serial number is supposed to be. So in particular, you know, your adversary could just honestly run the generation algorithm to generate a banknote and serial number, and then try to clone it. And you know, he chose the serial number, so he outputs it. And right now, if you could do that, that would violate the security of quantum lightning. So quantum lightning is actually a strengthening of quantum money that says that you basically get this unclonability property, even if the adversary generated the serial number themselves.
So in what sense is quantum lightning a strategy to justify security of quantum money?
I mean, it's not so much a strategy. It's just that, you know, in order to get around this this sort of conceptual barrier to proving the security of quantum money, this is an approach you might take is trying to design a quantum money scheme where your reduction has this property that it's inherent, that it's sort of probabilistic. And
I'm still a little unclear about what the conceptual barrier was, right? I mean, you know, like in some sense, you know, we did manage to prove the security of a, you know, quantum money scheme, you know, via some reduction. And just, you know, in our case, the problem reducing.
Good.
So it turned out not to be hard, but you know,
good.
You know,
So
relative to an oracle, it does work.
Right. So
how did we get around this?
You got around this by using an atypical modeling of security that cryptographers don't normally do. Right. So you, in your reduction, it was very sensitive to the running time of the reduction and the reduction success probability. Maybe not the running time, but certainly the success probability. It was, you know, no efficient adversary can solve some problem with probability more than you know, some precise exponential quantity.
That's right.
Right. So if you had your
Yeah, we just said, we needed to make a strong assumption about that,
right.
that the adversary cannot even succeed with this, large exponentially small success probability.
Right, right. So the reason that that doesn't, so that gets around this as well. And the reason is that basically what happens is because you're running your reduction twice here, you sort of you're sort of amplifying that exponentially small success probability to the point where this reduction actually doesn't qualify as as it will solve the problem, but it won't solve it with high enough probability to qualify.
Okay.
Now with usual cryptographic modeling of our hard problems, it's for all polynomial time algorithms, they have negligible probability. And there, multiplying whatever polynomial advantage your adversary had, you're going to square it, but that's still a polynomial. So in that case, this meta reduction still counts as an adversary for P. Whereas in your reduction, this meta reduction will actually not count as an adversary for P.
Okay, I'm still not clear. What is this picture supposed to illustrate? It's supposed to illustrate that there cannot be such a reduction, like.
Yeah, well, I mean, there can be, as we're talking about on the next slide, but it's illustrating a barrier to coming up with a reduction, because if you could come up with such a reduction, then your hard problem is actually easy. At least assuming your reduction has a certain form.
Okay, all right, fine.
Mark, can you restate what this reduction is doing?
Right. So I mean, I don't know what the reduction is doing. It's sort of a general reduction. But my meta reduction is running the original reduction twice on the same challenge from the hard problem. The original reduction is trying to take a quantum money adversary and use it to solve the hard problem. So it supplies banknote and serial number to an adversary, gets two banknotes that are supposed to be valid with that serial number back, and then based on whatever it got back, it's trying to solve the hard problem over here.
So I have a dumb question here. Each reduction is outputting two banknotes, or these are the two banknotes of one reduction?
Each reduction is outputting a single banknote, and then it expects two banknotes in return. This reduction, I'm just going to throw it away once I got my one banknote, and then this reduction, I'm going to feed the two banknotes from the two different reductions into it. Right. So yeah, I don't know if you want to call this a strategy or another primitive. Sort of, I talked about it as, I think both these works talked about it as a primitive, but it's an object that ends up being a strengthening of quantum money, but it doesn't have this inherent barrier, or not inherent, but it doesn't have this supposed barrier present anymore.
I mean, Mark, your quantum lightning paper did a huge number of amazing things, but before that paper, like, we had talked about quantum money that you generate and you can't generate the same one again. Right. So in what way is quantum lightning different from that?
So it's really the same thing. The prior work never really formalized it. Okay. So yes.
Are you claiming, like, formally that if you want to have like a black box reduction proof of security of quantum money, you have to do the stronger thing with quantum?
No. So there's the white spot here. So there's one more tile that I'm going to fill in. Right. So before getting into that, though, I wanted to mention an interesting open question. So I'm going to sort of sprinkle this talk with open questions. A lot of them are actually broadly accessible. So even if you don't like quantum, you can still think about some of these, and if you solve these, there's interesting consequences. So here's an open question that if you could solve would actually give you quantum lightning and therefore quantum money with hopefully provable security. So what you might call this a gap LWE. So it's going to look like learning with errors, but we're going to add something to it. So what I want is some sort of distribution over tall, skinny matrices, maybe with some auxiliary inputs, maybe not. So I want some distribution over tall, skinny matrices. And I want that relative to this tall skinny matrix, the short integer solution is hard. So you know, if I have a tall skinny matrix, what is a short integer solution? It's you want to find some vector that's in the left kernel where the vector is small. So my green vectors here are going to be short vectors in L2 norm. Right. So I want that cis is hard relative to this distribution, which means if I sample an A from this distribution, I give you A. I also give you maybe some auxiliary information about A, that it should be infeasible for you to actually solve cis. Okay. So certainly so far this we can do this based on the worst case lattice problem. A is just a random matrix and the auxiliary information is nothing. And then you just get plain old cis. The other thing I want is that search LWE is hard. So what is search LWE? It's I take a random linear combination of the columns and I add some short error to that. And what the search version of LWE says is they want you to find the secret S, which is the linear combination of the columns. Right, and again, so far there's nothing interesting or nothing new here. A random matrix also based on worst case lattice problems is the search LWE is hard. And actually, in fact, Regev's reduction between cis and LWE sort of allows you to go between these, or in particular, justify the hardness of search LWE based on the hardness of cis, no matter what your distribution over matrices. Okay, and so here's where things are going to get interesting. What I want is that the decision version of LWE, so search is hard. What I want is that the decision version is easy. So what is the decision version? It's I give you an LWE sample, or I give you a uniformly random vector, and you have to decide which is the case. Right. So now this is where things get interesting, and we don't know the answer. Right. So we know that a random matrix A, all these problems are hard. On the other hand, how do we normally break? In many cases, we can give a trapdoor for A that would allow you to break decisional or even search LWE, but those trapdoors are just cis solutions. And so what we need is some sort of way of generating instances of LWE where the decision version is easy, but that doesn't involve just like making cis hard and through a quantum reduction that would doesn't involve making cis easy or search LWE easy.
Mark, is there some kind of a win-win? So suppose that this does not exist, does it have useful consequences?
It's sort of related to this notion of sample preserving search to decision reductions, right? So we actually know for random matrices how to go between search and decision. They're equivalent. The reductions though change the matrix A. They sort of re-randomize the matrix A. And the initial reductions actually also expanded the matrix A and made it bigger. There was some work that showed actually you can sort of preserve the dimensions of the matrix A and still get the search to decision reduction to work. And if you could rule this out, basically what it means is you actually have a search to decision reduction that maintains the matrix A itself. And I don't know that there's any applications necessarily, but it's it might be an interesting.
Just tightening the connection between crypto applications and coding theory, right? Because in coding theory, they care about the search, and in crypto applications, we typically care about decisions. So it's
right. Yeah. So I think it would be, either way, whether this exists or not, I think would be an interesting result. I'm not aware of cryptographic applications of refuting this.
It's like a random and just gave you access to an oracle, like had a trapdoor and distinguish LW with a particular A.
I don't believe it's known. Right, and that would, yeah. Yeah, I don't believe it's known.
Seems like a bit of applications in
Categorical.
Yeah, it might. It's not something I've really thought about. What are the applications to a sort of a negative result here? But yeah, yeah, I don't know. This is one of my favorite open problems. Trying to come up with an instance like this. So, okay, so let's get back to our strategies to justify security. So the last strategy that we know is the following. We're actually going to not care. So we're going to actually say that our reduction doesn't care so much about the cloned quantum money state it got from the adversary, but really all it's going to care about is the fact that the adversary cloned. So put maybe a little more, or to put it in other words, what we're going to imagine is we have there's some real world where we have, you know, our public key and you know, the adversary is given a quantum money state, etc. And then there's going to be some fake world. And in the fake world, cloning is actually going to be information theoretically infeasible. So think about, like, there are certain like fake public keys relative to which cloning is information theoretically infeasible. And what the reduction is basically trying to do is just tell which world they're in. And so in this case, the reduction might actually have the ability to clone states. The reduction itself might have the ability to clone states as much as it wants. But the adversary in one case will be able to clone, and in another case won't be able to clone. And that is going to allow the reduction to distinguish the two cases and solve its problem.
What's the one known instance of this?
So the one known instance is, this is how I was able to prove that the Ernst-Cristiano quantum money scheme was secure if you used indistinguishability obfuscation. So in order to give the gist of that, I'll first describe the Ernst-Cristiano quantum money scheme. So the central object in the scheme are these subspace states. So A is some linear subspace of, let's say, half the dimension of the ambient space. And the banknote is going to be the superposition over all vectors in that subspace. The serial number, I'm going to change this in a moment, but the serial number for now, think of it as just the description of the subspace and also the dual subspace. You know, so certainly you can go from A to A perp and back, but we'll see why I wrote these down separately in a moment. And then how do we verify banknotes? So the first thing Vera does is it first checks that the quantum money state actually has all of its support in the subspace A. And this is just a classical test run in superposition. So this is easy enough to do when you're given A. And then, well, I should say, if you stopped here, your verification succeeds, but you don't have any security, because any classical string in the subspace A would also pass verification, and you can obviously copy any classical string as much as you want. So this isn't enough for security. And so what you do is you do the quantum Fourier transform. If you had the right quantum money state, it turns out that the Fourier transform gives you another subspace state, but it's a subspace state for the dual. And so you can just use your knowledge of A perp to check that your support is in fact all contained in the dual subspace. And then you just do a QFT back in order to get your quantum money state. Right. So this is the proposal. Now, as stated right now, it's totally insecure because the serial number, if public, tells you what A is, and given A, you can just use like basic linear algebra to construct the subspace states. So what Aaronson and Cristiano proposed is that, well, actually, you know, in order to do verification, I don't need to know the subspace. I just need to be able to test membership in the subspace A and membership in the dual. So, you know, why don't we obfuscate them in some way? So obfuscate membership in A, obfuscate membership in A perp. And the hope is that we obfuscate it in a way that somehow hides the subspace A, and in particular prevents you from actually constructing the subspace state. And then what Ernst and Christian do is they prove in a black box model that in fact this is secure unconditionally, and also gave the candidate instantiation that we talked about. Right. So the question, I guess, is what kind of security, forget oracles for now. If I were going to implement this using some sort of standard model obfuscation scheme, what is the security property that we need out of it? And maybe there's many security properties that would work. But here's one that's certainly sufficient. So it's something that I'll call subspace hiding obfuscation. Here's what the security stipulates. It says, okay, first choose a random subspace B of some dimension. I'm going to be kind of hand wavy about the dimensions. So first choose a random subspace B, and then choose a random subspace of B and call it A. And what I'm going to give to the adversary is either, so I'm always going to give the adversary A, and then I'm either going to give an obfuscation that tests membership in A or an obfuscation that tests membership in B. And what we want is that these two worlds are indistinguishable. Right. So so this is the the definition of subspace hiding obfuscation. And then if you have subspace hiding obfuscation, that's actually enough to instantiate the Ernst and Cristiano quantum money scheme. How do you do it? So, or what's the proof look like? So in the proof, okay, so here's your honest quantum money serial number. And remember the banknote is the subspace state for A. So what I'm going to do is I'm going to use the subspace hiding obfuscation security to define a fake world or an imaginary world where my public key actually is obfuscating some superspace of A, I'll call it S, and also obfuscating some superspace of A perp, call it T.
In this notation, when you say you give A and obfuscation of A, what do you mean by giving A?
I mean, so the adversary is trying to distinguish two values. What are the values? Are these pairs? One is
right. But A is given. How is it true?
No. Just in the clear. Just written as bits. Exactly.
So through some bases, you've actually specified what A is.
Yes.
Some compact representation.
Right. Exactly. And the reason A is here is basically, so there's kind of two obfuscations going on, right? There's one for A and one for A perp. And so in order to maintain security of the pair of them, you need some sort of composability of this definition and having this A sticking around. Right. The quantum money adversary is never given A, but we need our reduction to be able to actually, in order for our reduction to actually work, we need the reduction to know what A is. Right. So what happens? So we're going to define this fake world where instead of an obfuscation of A and an obfuscation of A perp, I give you an obfuscation of S and an obfuscation of T, where S is a superspace of A and T is an obfuscation, a superspace of A perp. And what's crucially important here is that when I do this in this fake world, the verification of the adversary's forgery is still with respect to A and A perp. So I give you obfuscations of S and T, but then I'm asking you without you don't know A, and I'm asking you to come up with a subspace state that is valid with respect to A and A perp. So these are the two worlds, and in this fake world, the adversary just information theoretically doesn't know A anymore. They know a superspace of A and a superspace of A perp, but there's some uncertainty from their perspective about what A is, and it's information theoretic uncertainty. And yet they somehow have to clone a state with respect to A and A perp. And it turns out now you can just use, you can in fact use information theory and show that this is just unconditionally hard to clone in this fake world. But then you can use security of the obfuscators, the subspace hiding obfuscation, to say that the fake world and the real world are computationally indistinguishable, and now you have your security proof. So if you could forge in the real world, you can forge in the fake world, but that is unconditionally impossible. Right. So this is basically the only other way we know how to justify the security of quantum money is through. So now I guess the obvious question is, I should also point out that in the reduction, so the reduction is trying to distinguish between the real and the fake world. In the reduction knows A, and the reduction knows A in order to actually implement the verification. So it knows A in order to come up with the banknote that the adversary sees in the first place, and then also needs to know A in order to implement the verification. And so because it knows A, it can clone all at once. But the point is, it knows that the reduction, it knows that the adversary doesn't know A. And all it's using in order to tell whether it's given an obfuscation of A and A perp or an obfuscation of S and T, all it's using is the fact that in one case the adversary clones, and in the other case it doesn't. And that's how it's. So it doesn't care, again, it doesn't care what the clone is. It's not really using anything about the clone, just the fact that the adversary cloned in the first place.
So it's ultimately not information theoretic. You're saying, if you could violate the
the ultimate proof is it's information theoretic in the fake world, but the fake world's not public key quantum money because you need A and A perp in order to verify. And then so you're using computation to just go between the fake and the real world.
Fine.
All right. So this gives me the second open question, which is, can you construct subspace hiding obfuscation from standard post-quantum assumptions? So we actually know how to do this from DDH. It's not hard, but the DDH is broken by Shor's algorithm. And so the question is, can you, from lattices, LPN, whatever your favorite post-quantum assumption is, can you construct subspace hiding obfuscation? And this is
I mean, what was it specifically about the subspace scheme that let you use IO? Like, would IO also work for other public key quantum money schemes?
No, not obviously. Yeah, so in the last 10 minutes, I was actually going to segue to talking about what we know about obfuscation. I won't really address that question.
We can talk about it later.
Yeah, I mean, I don't really address how the proof goes. It's sort of it is very particular to the subspace.
Okay, talk about it later.
Yeah, so I wanted to conclude the morning talk with a detour into obfuscation and what do we know about obfuscation. And the reason I want to do this is because obfuscation became a central object in classical cryptography, and for quantum cryptography and all these unclonable concepts that we'll be talking about. In many cases, the only way we know how to justify security of our constructions is if they're based on obfuscation. So, this seems like an important thing to make sure we have quantumly and so obfuscation is a really old concept, dates back many decades, and there's a lot of what I'll call ad hoc obfuscation schemes out there. And they just do sort of, simple transformations on program code where they, I don't know, insert or remove white space, reorder operations, insert dummy operations, stuff like that. And this ad hoc obfuscation gives software that's, impossible to read for a human. But it turns out in most cases with enough effort, you can actually sort of understand what the program is doing and recover something resembling the original program. And so we like to think of ad hoc obfuscation as more of a speed bump. It's not really secure in the usual cryptographic sense of secure against polynomial time adversaries. And then we have a more recent object that I'll call mathematical obfuscation. And here we're really doing transformations at sort of a mathematical level or circuit level. So here's a picture, like one of the early approaches to mathematical obfuscation was to use Barrington's theorem to write things as a matrix branching program. Then you do algebraic transformations on the matrix branching program. Mathematical obfuscation turns out actually gives us very strong guarantees, assuming it exists. And because of this, it's become a central object in theoretical cryptography. And I say theoretical because, as the cryptographers know, we're sort of still very far out in theory. Unfortunately, though, even if you have the best obfuscator in the world, there are just some programs that can't be obfuscated. So this, even before we had mathematical obfuscation, Barakit will show that there are some programs that cannot be obfuscated. And the rough idea is that they came up with programs where if you run the program on its own code, or if you run the program on any code for the program, it'll spit out the original program. So my fuzzy programs there mean it was obfuscated, and here the unfuzzy one. So I should mention that I'm not going to formally define what it means to be obfuscated. The point is that there are some programs out there that, this clearly violates anything you would want from an obfuscated program. And as such, we have to settle for something that isn't optimal in terms of security, and that's indistinguishability obfuscation, which says that if I give you two programs that compute the same functionality, then I hope that their obfuscations are indistinguishable computationally. The problem with indistinguishability obfuscation or I/O is that what does it mean in terms of I have some program. Maybe the original use of obfuscation before cryptographers got their hands on it was to protect intellectual property in software. So I have my program. I have some intellectual property that I want to protect. What does it mean to obfuscate it with I/O? I don't know. In order to demonstrate anything with I/O, you need to exhibit two programs that are functionally the same. And I have my one program. I don't know, how do I find out another program that computes the same thing? And even if I do, the fact that they're indistinguishable, what does that tell me about the protection of my intellectual property? I don't know. So I/O doesn't really have a meaningful guarantee on its own, though we do know if a program P can be obfuscated by any obfuscator, I/O is good enough. This is shown by Goldwasser and Rothblum. So in some sense, I/O is, and they coined this term, I/O is the best possible obfuscator. But that still doesn't really answer the question of, what are the guarantees, when can a program be obfuscated and what guarantees it has. Sort of a big change happened in 2013 with the first proposal of mathematical obfuscation. And then there are tons of works I can't possibly summarize. That would be a whole talk on its own. But sort of the main things for us today are that a couple of years ago, there was this breakthrough work by Jane Lin and Sahai that showed how to build I/O from somewhat standard tools, except they're pre-quantum. The tools they use do not have, or at least one of the tools they use does not have security against quantum attackers. So in the classical world, we actually have pretty compelling constructions of I/O. In the quantum world, things are not as good, but they're okay. So we have a few works that have proposed constructions of I/O, and these are really candidates, but they have been analyzed. There've been a number of works trying to justify the security of these, and they're they plausibly are post-quantum.
What makes them a candidate and not like a proper proposal?
These constructions are all based on lattices, but we don't know how to prove their security relative to any assumption that people have made on lattices.
Okay.
I think these recent works actually do boil down the assumption to something really nice and easy to think about, but they're certainly non-standard. And this one is just purely a candidate. It's just, here's a construction that we don't know how to break. Okay, so we have in the pre-quantum setting, we have these pretty convincing I/O constructions. In the post-quantum setting, we have ones that are seem quite plausible, but maybe a little uncertain. And then the other thing that's happened in the last 10 years is we have basically developed a number of techniques for using I/O to actually justify the obfuscation of specific programs. So basically, there's been all this work on using I/O to solve certain cryptographic tasks. And the way it works is that basically they design a particular program and then more or less prove that it can be obfuscated with I/O. And that gives you a lot of cryptographic applications. Oh man, you can't see my bubble. So there's a giant oval here. It's on the screen. Okay, good. So there's a giant oval here of all classical programs, and we know that there are some that are unobfuscatable, just unconditionally. And then we have provably obfuscatable programs on the other end of the spectrum, and sort of everything in between we don't really know. And it's a pretty vast area in between. And then if we zoom in on what we know how to obfuscate, there's basically 4 pieces. So down here are learnable programs. By learnable, I just mean given Oracle access to the program, you can recover the program. These are trivially obfuscatable just in the sense that you can just output the program in the clear, and it's it meets our definition of obfuscated in the sense that anything you can learn from Oracle access, you can also learn from the program code, vice versa. Anything you can learn from the program code, you can learn from Oracle access, because Oracle access gives you the program code. So these are sort of trivially obfuscatable. And then what we know from the last 10 years of work on applications of I/O is we know how to obfuscate a lot of cryptographic programs. And we also know how to obfuscate evasive programs. So evasive program, or some evasive programs. Evasive programs are those that basically are the set of inputs that are accepting are very sparse, and any particular input is unlikely to have caused the program to accept. So things like point functions and whatnot. So we have for a lot of evasive programs, we know how to obfuscate them. And then there's basically a little sliver of things that we know how to obfuscate that aren't learnable, cryptographic, or evasive. And that's exactly where subspace hiding obfuscation comes in. So it's non-evasive because you're given the subspace A, and all inputs in A will be accepted. So you can always find accepting inputs to your obfuscated program, and yet you're still hoping for some level of security. So it's not evasive. It's also not cryptographic. It's just hyperplanes. There's not, it's not like you're obfuscating PRFs or anything.
By a cryptographic program, do you mean one for a PRF?
Like a PRF, yeah.
Right. And wait, and those can be obfuscated by?
Well, okay, not all cryptographic programs can be obfuscated. You can come up with PRFs that cannot be, but many cryptographic programs can if they're designed carefully. And this was sort of, essentially the last 10 years of work on applications of I/O has, what they've shown is how to design programs that can be obfuscated, and they all tend to be cryptographic.
All right, thank you.
And here, when we obfuscated, is about VBB. Or
I'm being very imprecise. Like subspace hiding obfuscation is not actually as strong as VBB. VBB is stronger. I don't really have, but I don't really have a precise definition of what I mean by can be obfuscated, but think VBB or related things. Right. The point I guess is that I/O on its own doesn't say anything. Like I can I/O any program, but that doesn't imply anything is hidden about the program. What I mean by these is that something is hidden about the program given its code, something non-trivial.
So, Mark,
Yeah.
So the connecting round and the barrier construction is for subspace hiding obfuscation that's evasive, right?
I might actually be right. I don't remember if their work considers any setting that's non-evasive.
Yeah, I thought that it's just extension of point functions so that you cannot really know the subspace inside.
But they prove some sort of VBB. And if the VBB is with auxiliary information, then you're probably.
If it's not evasive, then it's learnable.
No, subspace is not though. Oh, okay, so I don't know. I don't know what.
It's a big enough subspace, and you can make membership where you can learn.
Sure, but think of it like the dimension of subspace is like half or 2/3 of the overall dimension, and it's sparse. But you might be given side information that tells you accepting inputs, right? So in that sense, it's not evasive anymore. That you're given accepting inputs, but what you still want is some security for the points that you don't know, right? So it's very close to an evasive function, but I guess I don't consider it evasive. And for example, in here, in this group here, we can obfuscate subspaces using compute and compare obfuscation. We can obfuscate subspaces if you're not given anything about the subspace, right? But once you throw in the fact that you're actually given a smaller subspace explicitly in the clear of inputs that are accepting, then we don't know how to do this from other than IOs.
So the two notions of subspace of hiding obfuscation is different in the two notions.
Yeah, I mean, I don't remember exactly what they prove. I thought that theirs would have encompassed subspace hiding obfuscation, but certainly it's kind of a trivial proof that proves that DDH gives you subspace hiding obfuscation. Right. You just have a matrix whose kernel is your subspace.
Yeah.
And it's really easy. So what they prove allows you to do maybe it's incomparable to subspace hiding obfuscation, but it's certain it's some sort of VBB notion that's a stronger security property.
If you connect the notion of subspace hiding obfuscation that you need for quantum money from groups, isn't that strictly better?
Well, the groups are pre-quantum, so you don't get a secure quantum money scheme. Yeah. Okay. Yeah. So I should mention that I'm not claiming that there's nothing else in this little sliver here, but I'm actually not aware of anything, or maybe I just forgot and I was aware. But I if there's anything else that we know how to obfuscate that's not cryptographic, not evasive, to share. And this leads me to the third open question, which is, I don't know, I feel like the non-evasive, non-cryptographic setting is actually, for the original motivation of obfuscation of protecting intellectual property, that is the setting that you're usually in, right? Whatever software I develop is probably non-evasive, otherwise it's not particularly useful. And it's probably not cryptographic in nature. And so sort of finding more ways to justify that you can securely obfuscate non-evasive, non-cryptographic programs. This is like a pretty open-ended question, but I think this is a very interesting one. Perspective of just like understanding what you can see. So I'll just so the takeaways here are that we have somewhat compelling pre-quantum IO. We have good candidates for post-quantum IO, but their status isn't quite as good. Then we have a good understanding about the guarantees of IO for some cryptographic or evasive programs, but not a lot else. And there's really not a great understanding of what you can obfuscate securely, even if you had IO, what you can obfuscate securely in the non-crypto or non-evasive setting. So I think with that, I'll stop the morning talk. So we've talked about quantum money, and now in the afternoon we'll talk about copy protection and revocable cryptography, and everything about obfuscation that we've talked about will be relevant for copy protection as well. I'll leave it here, and we'll come back later.
All right, so we will reconvene at 1.